Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. We're going to continue solving 2x2 linear systems of equations, and we're going to take a look at the second algebraic approach. It's called elimination, or sometimes addition, as you'll hopefully soon see why. The elimination method works based on this fact, that if you have two things that are equal, A and B, and then another pair of things that are equal, C and D, well, if you add A plus C, that's going to be the same as if you had added B plus D, because, well, A equals B and C equals D. So what we want to do is this. When using elimination, if you do not already have both of your equations in standard form, then rewrite them in standard form. And then if you can, lining up x's with x's and y's with y's, if you have things with coefficients that are opposite in sign, you could add up the like terms along a column and cancel them out. If they are not opposite in sign, like 2x and negative 2x, then we may need to multiply one or both equations by a constant number before we can do the addition along the columns of like terms. Once you've found the solution to one of the variables, solve for the other variable as well, so that you get your xy ordered pair that's a solution to the system. Here's our first system to solve. And in this case, they are both already in standard form, and we have the coefficient of x. We have opposite signs there, 8 and negative 8. So that if we combine those like terms along a column, we're going to get cancellation. We've eliminated x. Now add 2y and y to get 3y. And on the other side, 0 and 12 to get 12. We can solve this for y. See, what we've done is we've boiled this 2x2 system down to one equation with one variable, divide both sides by 3, and we get that y equals 4. You could go back to one of the original equations. In this case, it would be easier to plug y into the second one. We have that y is 4. Subtract 4 from both sides. Get negative 8x equals 8. Divide both sides by negative 8. And we have that x is negative 1. So that tells us x is negative 1 and y is 4. If we were to compare this to solving graphically, we would have seen them intersecting at the point negative 1 comma 4. It's also a good idea to do a check. Since I got, after finding out that y equals 4, that x equals negative 1, I got that from the second equation. I'm going to do a check with the first equation. So 8 times negative 1 plus 2 times 4. I want to see if we come up with 0, and multiplying before I add, we do in fact get that 0 equals 0. Unfortunately, in this example, if we add up 5x and 7x, we get 12x, so x is not eliminated. And if I add y and negative 3y, I get negative 2y, so y is not eliminated. What we're going to need to do here, if I label this as equation 1, and this one is equation 2, we do have opposite signs here. If only I had a positive 3y to cancel the negative 3y in equation 2. Well, I could multiply every term on both sides of equation 1 by 3. positive 3. That has to be done to all terms on both sides. Now I can add that to equation 2. It's going to give me 22x. The y's cancel because we've got 3 and negative 3 as coefficients. And negative 39 minus 49 will give me negative 88. Dividing both sides by 22, I'll get that x equals negative 4. Going back to the original equations, just in case I made a mistake here, I'm going to plug in negative 4 in one of the original versions. And I've got a smaller number here for a coefficient and a nicer small coefficient on y as well. So 5 times negative 4 plus y equals negative 13. Gives me negative 20 plus y equals negative 13. Add the 20 to both sides. Negative 13 plus 20 is 7. And since I got that from equation 1, I will plug both into equation 2 to do a check. 7 times negative 4 minus 3 times 7. I want that to be negative 49. And it is. So our solution, negative 4 for x and 7 for y, as an ordered pair in case that's asked for, parentheses negative 4 comma 7. As with the previous example, if we add the x's, we get 7x, so it's not eliminated, and we'd get 7y, so we don't get elimination there either. So not only am I going to have to multiply one of the equations, but there's nothing nice to multiply 2 by to get 5, or to multiply 3 by to get 4, and vice versa, to multiply something by 5 by something to get 2, or to multiply 4 by something to get 3. It's not going to happen. So I'm going to consider the least common multiples of the coefficients of x, 10, and of y, 12. 10 is smaller. I would like to get a 10x and a negative 10x in those equations. So I'll multiply the first one by 5 and the second equation by negative 2. Again, remember that you have to multiply all terms on both sides by that number. That's going to give me 10x plus 15y equals 20. And in the second one, multiplying all of those by negative 2, negative 10x minus 8y equals negative 6. Now I can get the 10x and the negative 10x to cancel. 15y minus 8y is 7y. 20 minus 6 is 14. Divide both sides by 7, and I get that y is equal to 2. So going back to one of the original equations, and I've got the smaller number there, I'm going to plug in to equation 1 what I've just found for y. And solve that for x. Do the arithmetic there. Subtract 6 from both sides. 2x is equal to negative 2. Divide both sides by x equals negative 1. It looks like we have a solution of negative 1 comma 2. x comma y. But checking that, since I got that from the first equation, I'll plug both of them into the second. I want the left-hand side to equal to 3 on the right-hand side. 5 times -1 plus 4 times 2 is -5 plus 8, which does give me +3 as I wanted on the right-hand side. So -1 comma 2. X is -1 and y is 2. That is the solution. In this example, we do not have both equations in standard form. The first one is, but the second one is in slope-intercept form. So, first of all, I could add 2/3 x to both sides on the second one. Now, what I could try to do is multiply everything in the second one by -6 to get 6y there, although dealing with this fraction could be interesting. Turns out it's actually not going to be that much of a problem, because the denominator of 3 will go into the 6. Again, remember that we have to multiply every term on both sides by that same number. 3 goes into 6 twice, still negative though, so -2 times 2x minus 6y equals -12. And -2 times 2x is -4x. That's our rewrites of equation 2. So now we have equation 1. We haven't done anything to change that. I'm getting -4x minus 6y equals -12. In that case, not only do the y's cancel, but the x's cancel also. What are we left with on the left-hand side then? We're left with 0. On the right-hand side, 12 minus 12 is also 0. And that's a true statement. Our conclusion when we saw something like that with substitution was that if all the variables dropped out and we get the same number, same number, same line, if this was being done graphically. But if that's the same line, then every xy ordered pair that is a solution to the first equation is a solution to the second equation as well. And so we have infinitely many solutions to the system. On the other hand, we found out with the case where all the variables drop out, but you get two different numbers that are unequal, that there are no solutions. Graphically, you would be seeing parallel lines. You couldn't have 0 equaling some non-zero number, for example. So let's see what happens there. This system of equations we've seen previously in solving both by graphing and substitution. So what's it going to look like when we solve by elimination? I have the x's. We've got different signs. That's good, although it's not -4 and +4 or -2 and +2. And it's similar with the coefficients of y. In the case of comparing what would be the nicest, well, if I just multiply this by 2, I will have a -4. If I multiply this by 2, I'll have a +6 to match up with a -6y. So either way, multiplying by 2 seems to be the best. So equation 1, equation 2, multiply 1, the equation 1 by 2. Again, remember to do that to all terms on both sides, and we will get -4x plus 6y equals 48. So I multiplied all terms, both sides, by that same number. And I will copy down equation 2. When I add the x terms along the column, zeros out, this zeros out, together the total, 0 on the left, but we add 48 plus 12 and get 60. Untrue statement, 0 is not equal to 60. So that must mean that there are no solutions to this system.